Hello, rising 7th graders. We're going to revisit a topic from late in 6th grade. In this particular video, we're going to focus on the multiplication and division of integers. Integers, of course, are the whole numbers, 0, 1, 2, 3, 4, 5, and so on, together with their opposites. 0 is its own opposite. The opposite of 1 is -1. The opposite of 2 is -2. So, integers. The integer operations are something that you all know very well, but we're going to solidify your knowledge, review, and get you very much to have faith in what you're doing when you, in this case, multiply and divide with integers. Of course, as we learned, multiplication and division is easier than addition and subtraction in terms of the sign because the rule is so easy to state. When you're multiplying two numbers, if the signs are the same, the answer is positive. And if you're multiplying two numbers and the signs are different, the product is negative, right? So positive times positive, negative times negative. The signs are the same. The product is positive 12. Over here, the signs are different, a negative and a positive and a negative. Different signs, the product is negative. In the second part of this video, we're going to prove why that's true. And that's to give you that solid faith that what you're doing is correct. But before we do that, we're going to connect division to this. And one of the beautiful things about learning mathematics is that often when you learn something in the lower grades, as you expand your knowledge and bring in other kinds of numbers, the rules are still the same. We have up here 4 what we might call facts. You learned in 3rd grade that when you're dealing with multiplication and division, if you know one fact, you know 4 of them. So let's go through that for each of these. We'll expand from 4 facts to a total of 16. And the next fact is also a multiplication fact. Multiplication is commutative. So we also have 3 times 4 equals 12. And we frequently, what I'm about to do in expanding to 4 facts, it's very common in the lower grades to call what we're doing finding a fact family, a family of facts. I still call it that. And it works even when negative numbers are involved. So there are 2 division facts that go along with these 2 multiplication facts. And of course, we're going to take the typical middle school approach of indicating a division with a fraction bar, indicating a division as a fraction. So we have 12 divided by 3 is 4, and 12 divided by 4 is 3. So there are the 4 facts that all flow from 4 times 3 is 12. Why are these 2 up here correct? Because a division is a question about multiplication. This is asking us right here, 12 divided by 3, we're being asked, what can you multiply 3 by to get 12? And the answer, of course, is 4. This division question is, what can you multiply 4 by to get 12? And the answer, of course, is 3. So there's the fact family that you all knew in 3rd grade. Let's look down here. Well, with negative numbers involved, multiplication is still commutative. So we also have -3 times -4, positive 12. But we also have 2 division facts. We have 12 divided by -3 equals what? I'll put it that way for now. And 12 divided by -4 equals what? Well, just as you did in 3rd grade, refer back to the multiplications. This is asking us, what do you multiply -3 by to get 12? And of course, the answer is -4. You see that both of these multiplication facts here. This is asking us, what do you multiply -4 by to get 12? And the answer, of course, is -3, as the 2 multiplication facts show. Beautiful thing that we still can talk about fact families even when the negative integers are involved. And I'm going to come back to this in a moment. I'll put this here to remind me, and I'll just put ruled question mark. And this is also a beautiful thing that we're going to emphasize when I'm done with the rest of these. Over here, multiplication is commutative for all numbers. So here we can have 3 times negative 4 also being negative 12. And 2 division facts. Negative 12, this product, divided by 3 equals what? And negative 12, the product, divided by that negative 4 equals what? This is asking us, what do we multiply 3 by to get negative 12? What do you multiply 3 by to get negative 12? And the answer, of course, is negative 4. And you can see that in these multiplication facts. 3 times negative 4, negative 4 times 3 is negative 12. This one is asking us, what do you multiply negative 4 by to get negative 12? And the answer is 3. Right? The answer is 3. Here we have the 2 factors again. 2 factors are 3 and negative 4, 3 and negative 4, negative 4 and 3. So negative 12 being the product. The product is here on top of each division. See, but everything flows. From one of these, you can get all 4, just like you did in 3rd grade. Down here, we can use the commutative property of multiplication to write negative 3 times 4 is negative 12. And then we have 2 divisions. We have negative 12 divided by 4 equaling what? And negative 12 divided by negative 3 equaling what? This is asking us, what do we multiply 4 by to get negative 12? And the answer is negative 3. Over here, we're being asked, what do we multiply negative 3 by to get negative 12? And the answer is 4. You see the same 2 factors, a 4 and a negative 3. A 4 and a negative 3. So there you go. 4 fact families. Each family contains 4 facts, just like in 3rd grade. But now, what about this rule? Well, I've already reminded you of the rule for multiplication. When you're multiplying 2 numbers, when the signs are the same, the answer is positive, and when the signs are different, the answer is negative. Beautifully, the rule is the same for division, which shouldn't surprise you because when I presented the divisions just now, I was presenting them as questions about multiplication. When you're dividing 2 numbers, if the signs are the same, the answer is positive. And if the signs are different, the answer, quotient in the case of division, the signs are different, the quotient is negative. So let's make sure each of the divisions show that. Well, obviously the positive ones, signs are the same, the answer is positive. And down here, the signs are different for the division. With the multiplications, the multiplication here, of course, the 2 multiplications, the signs were the same and the answer is positive. But the divisions that go along with them have different signs. The positive 12 and the negative 3, that's different signs, so the answer is negative. And here, the signs are different in the division, so the answer is negative. We move up to the right side over here. Negative 12 divided by 3, signs are different, the answer is negative. Here we have negative divided by negative, the signs are the same, so the answer is positive. Here we have different signs, negative divided by positive, different signs is negative. Here we have the same signs, negative divided by negative is positive. So, bottom line here is, and please make sure before you move on from this portion of the video that if we can accept the rule for multiplication, then the rule for division has to be, it turns out to be the same rule, same sign positive, different sign negative, based on the definition of division. You know, let's take this one as an example. You could say, all right, negative divided by negative, the signs are the same, so the answer is positive. But you can also see it in this way. This number, the quotient here, you have to be able to multiply it by -3 to get -12. So what is that number? What is the number you can multiply -3 by to get -12? And it's 4. So the point I'm trying to make is you don't really need a rule for division. It turns out to be the same rule as for multiplication. But if you accept the rule for multiplication, the divisions automatically work out in a way that the rule is the same. So study this, make sure you agree with it, understand it all, and in the remaining portion of this video, what we're going to do is we're going to see what is behind the rule for multiplication. And then the rule for division flows from that, as I just indicated. So we only have that one last thing to do. Why is it that when you multiply two numbers with the same sign, you get a positive, and when you multiply two numbers with different signs, you get a negative? We're going to prove that. There is something that is true in mathematics that you learned no later than 3rd grade. When you multiply a number by 1, you get the number. The number 1 is therefore called the identity for multiplication. When you multiply a number by 1, you get the identical number back as your product. So 1x equals x. In Roman numerals, of course, this is a false statement. 9 does not equal 10, but this is not Roman numerals. This is 1x equals x. You've known that since 3rd grade and probably even earlier. This is what we're concerned with now. This is really what leads to the multiplication rules and the division rules, as we saw before. The division rules flow from the multiplication rules in terms of the signs. If we can prove that -1x equals the opposite of x, we'll then, in the very end of this video, show that that leads to the rules that we all know for multiplication. But when we're learning mathematics, it's not enough to know how. You know, the how in this case is when you're multiplying or dividing two numbers, when the signs are the same, the answer is positive. When the signs are different, the answer is negative. That's the how. This is going to lead us to the why. We're trying to prove that when you multiply a number by -1, you get the opposite of the number. Now, before we proceed to that proof, let me just indicate, it seems natural, doesn't it? Doesn't it seem natural that if 1 times x is x, then -1 times x is the opposite of x? That shouldn't surprise you. It's what we call intuitive. A lot of the things that we learn in math are intuitive, not all of them. I could give you a few examples right now, but as you go forward, there will come times when you learn something in math and it just doesn't seem, that's not what you expected. It doesn't seem right initially, but then as we go forward and learn, you'll convince yourself that it is in fact this way, even if it didn't seem that it should be at the beginning. But this probably seems right to you right now. I'm not going to, force you to believe that right now, but the proof is going to do that. So this is our goal to get to this point, to show that when you multiply a number by -1, you get the opposite of the number. So we're going to begin with two things we're going to assume are true. First, given a number x, we put that minus sign in front of it, and we get the opposite of x. When you put a minus sign in front of x, it's the opposite of x. And the other thing we're going to assume is that when you add two opposites, you get 0. X plus the opposite of x is 0. This, again, is something you've known for a long time. And just very briefly, let's say we're trying to add 3 and negative 3. Well, we think of 3 as a vector that begins at 0 and extends to the right so that the arrow there ends at 3. And negative 3 is a vector that starts at 0 and extends to the left and to negative 3. And when we add numbers, we add their vectors, and you add a vector by putting beginning point on top of end point. The beginning point is the point, and the end point is the arrow, right? So you take this negative 3 and move it so that it begins here at 3, comes back 3 units, excuse me, and there you are at 0. And addition is commutative, so we could have also taken, what did I do before? I moved the negative 3. We could also have moved the 3, this vector that represents positive 3, just move it so that its beginning point is at the end point of that vector, and it's going to extend 3 to the right, so once again we end up at 0. So opposites add to 0. And now we get to the beginning point of the proof. Let's just consider this thing. X plus negative 1 times x equaling 0. Right? Before we do anything else, I want you to notice this. Those two equations are the same, except up here we've got the opposite of x, and here we have negative 1 times x. And remember, we're assuming that this is true, that when you add two opposites, you get 0. We're assuming that that is true. Well, if we can prove that this statement is true, then negative 1 times x has to be the opposite of x, because it's in the two are in the same position of that same equation. Let me say this. The only number that you can add to x to get 0 is the opposite of x. The only number that you can add to x to get 0 is the opposite of x. So down here we have x plus something equals 0, so that something has to be the opposite of x. And before you go any further, just make sure you understand that if we can now prove that this statement right here, this bottom one, is true, then we have proven that negative 1 times x equals the opposite of x, and that's our goal. That's going to allow everything to fall into place for multiplication and, of course, division. So, ladies and gentlemen, how are we going to set out to prove that this equation here, this statement that x plus negative 1 times x equals 0 is true? If we can prove that this is true, then we've proven that negative 1 times x equals the opposite of x. First thing I'm going to do is rewrite the statement this way. 1x plus negative 1x equals 0. Now, what have I done there? What allows me to, well, there's that Roman numeral 9 again. It's not Roman numeral 9. It's 1x. What allows me to do that? Whenever you're proving something in math, you have to use things that you've either proven before or just agreed is true. Assumptions, definitions, basic assumptions that we can all agree to, definitions that we provide, or things that we've proven in the past. Those are the things that we can use when we're trying to prove something. So 1x equals x. I had that on the board before. That's true. For any number x, if you multiply by 1, you get x, the identity. So we've just used something and going from this line to this line, we've used something that you learned in third grade. What comes next? Well, the distributive property, or as I often say, the distributive property backwards. If you look at these two terms, these two things that are being added together, you've got 1x and you've got negative 1x. Well, they both contain an x. Both of those terms contain an x. So you can use the distributive property, which is true for all numbers, to rewrite the statement this way. 1 plus negative 1 in parentheses times x equals 0. And I'm just going to put here dp, or maybe I'll remind you about the dp. The distributive property says that a times b plus c equals ab plus ac. The distributive property is incredibly powerful and useful in mathematics. Since multiplication is commutative, the distributive property is usually written like this, but you could also write it as b plus c in parentheses times a, and this is just the commutative property. The a and the parentheses can switch positions, and this is also ab plus c. So the distributive property allows us to go from here to here. The distributive property backwards. We also refer to this process going from here to here as factoring out the x. Factoring out the x. We've got an x here and an x here. We bring it outside the parentheses. This is something we do a lot in Algebra 1, for example. But whenever I'm teaching this idea of factoring out a common factor from each term, I usually refer to it as the distributive property backwards because that's all it is. So now, look at what we have. We have 1 plus negative 1 times x. 1 plus negative 1 in parentheses. Well, what is that? One of our assumptions is that when you add opposites, you get 0. So this is 0. 0 times the x that we factored out equals 0. Okay? Now, how do we go from this line to this line? Well, opposites add to 0. I wrote it up there, right? Opposites add to 0. And we haven't mentioned this yet, but in third grade you also learned that when you multiply any number by 0, you get 0. It's the 0 property for multiplication. 0 times x is 0. 0 equals 0. A true statement, right? And what allowed me to go from this line to this line? Well, anything, let's call it anything times 0 is 0. Through a series of steps, things that we agree to. That's always how mathematics works. We build on what comes before. So everything that I wrote over here, we've agreed to in the past. You learned about the distributive property in third grade. It's very powerful. Through a series of because of reasons that we all agree to from the past, we went from this, x plus negative 1 times x equals 0, to 0 equals 0, a true statement. This is true. This is true for any x. That's what all of this shows. And once again, let me go back and put those red boxes in again. Because we have now proven that this is true, this statement right here that says consider, right? It must be true that negative 1 times x is the opposite of x, because so here, x plus something is 0. The only thing you can add to x to get 0 is the opposite of x. So negative 1 times x equals the opposite of x. We've just proven that, and now we're going to show why it's so important. We've come back to where we started. These four facts. You know? Over here on the left, we have same sign, positive, and over there on the right, we have different signs, negative. Let's now prove why that's true. Well, we don't have to prove this one. You should have also come to an understanding of why 4 times 3 is 12 in third grade. It's repeated addition, right? 4 times 3 means 3 plus 3 plus 3. And you can literally count or move along the number line. Oh, I'm sorry, 4 3s added together. 3 plus 3 plus 3 plus 3. Brings you to 12. So we gain that belief and understanding in third grade of why 4 times 3 equals 12. Well, how about negative 4 times negative 3? Well, we're going to use what we just learned a couple of different times. So here we have the opposite of 4. How can we rewrite the opposite of 4? We can rewrite it as negative 1 times 4, right? When you multiply a number by negative 1, you get its opposite. So when you multiply 4 by negative 1, you get negative 4. Let's do the same thing to negative 3. Negative 1 times 3. We're just rethinking each of those numbers in terms of negative 1 times 4 being negative 4, and negative 1 times 3 is negative 3. Now you might say, well, aren't we just using the rule for multiplication here? These are different signs, so it's negative. These are different signs, so it's negative. Well, that's true, but we don't have to use that. You can't really use what you're trying to prove in the proof. But because we just proved that when you multiply a number by negative 1, you get its opposite, we can rewrite negative 4 as negative 1 times 4. And we can rewrite negative 3 as negative 1 times 3. Okay? So I'm not using the rule to prove the rule here. I'm using that crucial fact that we proved, that negative 1 times a number is the opposite of the number. Now there are these things in all of the textbooks, in the lower grades, and they continue into the middle school grades. We've already talked about one of them, one of these rules, the commutative property of multiplication. The order doesn't matter when you're multiplying two numbers. Well, there's something slightly different called the associative property of multiplication. Also works for addition. The commutative property and the associative property work for both addition and multiplication. The associative property is a little different. That says we can associate or group numbers any way we like when we're multiplying. There's actually a demonstration or a proof, which I'm not going to get into now, where if you take the commutative property of multiplication and the associative property of multiplication together, you can just arrive at this simple conclusion. When you're multiplying a bunch of numbers together, you can do it any way you want. Any order, any grouping. So let's do this. Negative 1 times negative 1 times 4 times 3. I just took these four numbers and regrouped and ordered them. Took the two negative ones and put them here. Took the 4 and the 3, put them here. Same numbers. Let's now multiply the 4 times 3 first. We can do that. 4 times 3 is 12. Now, negative 1 times negative 1. Well, you know according to the rule that it's 1, right? A negative times a negative is a positive, but we can't, see, we're in the process of demonstrating, proving why the rules work. So we can't really use that. But we can use the fact that when you multiply a number by negative 1, you get its opposite. So let's think of this as the number. Let's think of this negative 1 as the x, or the number. We are multiplying negative 1 by negative 1. So negative 1 times a number is the opposite of the number. Negative 1 times negative 1 is 1. Right? Negative 1x equals the opposite of x. So here's this -1, and this -1 is like the x. -1 times x is the opposite of x. Well, so this is the x. What's the opposite of -1? The opposite of -1 is 1. So these two multiply to 1. Not because of the rule, because that's what we're trying to prove, but because we've proven that -1 times a number is the opposite of the number. So -1 times -1 is +1, which is the opposite of this -1 here. And 1 times 12, of course, is 12. Okay, please understand something, ladies and gentlemen. Here's a big way in which math works. We spend a lot of time proving things, or let's put it this way. We spend a lot of time convincing ourselves that something must be true. Then we're free to just use it. I am not suggesting at all that you're ever going to do this in the middle of a problem. In the middle of a problem, when you encounter -4 times -3, you're going to write 12. But because we've spent the time to understand why it's true, you're going to believe in it, you're going to trust it, and you'll remember it. It's not just something that I'm forcing on. Remember all of these things. No. Believe in these things, and you will remember them because you trust them, and they're deep in your long-term math memory. Let's move on. -4 times 3 is -12. We claim, according to the rule, that's true. Well, let's rewrite -4 as -1 times 4 and then times 3. We have already proven that when you multiply a number by -1, you get its opposite. So -1 times 4 is the opposite of 4, which is -4. And the associative property tells us that we can multiply the 4 times 3 first if we want. So we have -1 times 12. 4 times 3 is 12. So once again, we're applying what we proved over and over again. So -1 times 12 is the opposite of 12, which of course is -12. And this one's very simple. This is the most complicated one. And this is the one that usually is the one that's the hardest to believe. Why is a negative times a negative a positive? Well, that's what all of this is about today. Over here, 4 times -1 times 3, right? We can rewrite the -3 as -1 times 3. -1 times 3 is the opposite of 3, which is -3. And the associative property allows us to put the -1 out here, then the 4, and then the 3. It's very similar to the one above. -1 times 12 is once again -12. When you're multiplying or dividing any two numbers, when the signs are the same, the answer is positive. And when the signs are different, the answer is negative. I don't think you're going to forget that now. You already knew it before you watched this video. But now, you believe it, you trust it. This is the nature of mathematics. I think we've said enough about this for now. And play this video as often as you need to truly understand it on a deep level, and then use the knowledge automatically and mindlessly. We have to do certain things mindlessly without devoting a lot of our mental attention to it, because as you know, we're going to be solving equations that have several steps to them. So you can't get bogged down thinking about what happens when I multiply two negatives, or what happens when I divide two negatives, or what happens divide a negative by a positive, and so on. These things have to be right there for you to use to get through more complex problems. And my whole approach to teaching mathematics is to get that why. that firm understanding down so that we can then just sort of leave that behind and do things very easily, so that when those easy things, like these rules, are part of a more complex problem, we can succeed. So take care for now. It's been a pleasure.